Week 3 video assignment by Basit Alias, student number 2188967795. So the question was that this nitrogen gas in 5-meter cube tank at 120 Kelvin and 1 megapascals. So we have to determine the mass assuming ideal gas, what is the mass using the compressibility factor, and what is the error. So in given schematic diagram, so we first draw the diagram in which there is a rigid tank and it is closed and there is nitrogen gas in it. The volume of the tank is 5-meter cube, the temperature is 120 Kelvin, and the pressure is 1 megapascals. So these are the things which are given in the question. And then there are some assumptions. One of the assumptions is that the volume stays constant because the tank is rigid, so it doesn't deform, which decreases its volume, and also it is a closed system, so the mass of gas remains constant. And as we're using the ideal equation, so we have to assume that nitrogen behaves as an ideal gas. So in analysis, so to find the error, we must know the original mass. So to find the original mass, we're going to use the volume and specific volume values. So as specific volume is equal to volume over mass, so we just do a replacing and shifting in the equation, which makes mass is equal to volume over specific volume. Volume is given in this question, which is 5-meter cube, and the specific volume is 0.3117 meter cube per kilogram, which is in the appendix given in the question. So we get the mass 160.41 kg, which is present in the tank. Now the mass assuming that it is an ideal gas. So we have defined a system. Our system is the nitrogen in the tank. So the equation we're using is PV is equal to mRT. So we're using Mi, which means the mass as an ideal gas. So the pressure we have is 1000 kilopascals. So for this we have to convert from megapascals to kilopascals. Volume is 5-meter cube. The R is 0.2968 kilojoules per kg Kelvin. We get it from table A1. And the temperature we have is 120 Kelvin. So we use the equation, we make mass as a subject, and then we find the mass, which is 140.39 kilograms. So now we have to find the error percentage. So in error percentage, you use the original mass, you subtract it from the mass we found from the equation we used as an ideal gas equation, and we divide it by the original mass, and then we multiply it with 100 to get it in form of a percentage, and then we get 12.5% as the error using the ideal gas equation. Then we use the mass using the compressibility factor. So for compressibility factor, we have to find Z first. So for that, we have to find the critical pressure and the critical temperature. So we use the table A1 to get 3.39 megapascals for pressure value, and for temperature at critical point we get 126.2 Kelvin. And then we use the reduced pressure and reduced temperature formula, which is the pressure or temperature given in the question divided by the critical temperature and pressure we found from table A1. So we got for pressure reduced 0.295 and for temperature reduced we got 0.951. So these are the two values we got, and now we have to use as the pressure is between 0 and 1, so we have to use the figure A15A. So we get Z is equal to 0.87, and in the next slide we will see that how we find the Z. So from x-axis we see where the PR is. So our PR was 0.295, and we draw a straight line above, and then we saw where our TR was, which is reduced temperature. So our reduced temperature was 0.951, so we approximately take 0.95 as the line, and then we saw the intersection, and it was at 0.87 on the y-axis, which is the compressibility factor. So now we know our compressibility factor, so we'll use the equation, which is PV is equal to ZM RT. So we put MC, C means for compressibility factor, so we're finding the mass using compressibility factor. So it is, we take ZRT to the other side, so PV over RT is same as what we did in ideal gas equation, so we can use the same value, which was 140.39, and then we divide that with Z, which we got 0.87 from the previous chart, and our mass is 161.36 kg. So this is the mass we have found out by using the compressibility factor. Now moving towards the hour, so we subtract this mass from the original mass and divide it by the original mass, we get the hour, and to get it into the percentage we simply multiply it by 100, and we get 0.59% error in our result compared to the original value. So the comments on the result is simple. We can clearly see that the error was very low using the compressibility factor, which is 0.59, which is even lower than 1%. But the error using the ideal gas equation was really high. It was around 12.6 something, which is above 10%, which is a lot, which shows that the nitrogen is not acting as an ideal gas in these conditions. And this also shows that the compressibility factor is more reliable and accurate in finding the mass for the gas instead of using the ideal gas equation. Thank you.